Howdy, everybody. Hope you're doing well whenever you are. We're here for day 11 of Advent to Code. We're coming to an end. It's 2 days left. Well, I mean, one day. You've solved day 11. What should I say about today? For me, it actually turned out to be pretty easy, and I think it's just because I've done a lot of graph stuff. So, if you're familiar with graph theory and dynamic programming, part one and part two were essentially the same, where part one or part two was just like kind of an extension of part two. And the funny thing about it is like, I mean, I don't think you can do it any faster, but I suspect there's a way to determine like what order you go through the graph. But I was just all like, I'm just going to try. There's only two possible ways to go through the graph. So I'm going to try those two possible ways and just see what, sum them up, and boom, you're done. But I suspect you'll struggle if don't have a lot of knowledge of graph theory, or maybe you're fairly new to dynamic programming and it may be hard to like kind of reason about and come up with how to get there. So that's what we'll talk about today is dynamic programming plus graph theory. We'll look at the thing, see how to combine those two things to kind of like solve them. Just as a note too, we had talked yesterday about Z3, and I really wanted to learn more about Z3 to get into it. I actually think it's pretty cool, especially from the Rust perspective, because you can, at least the newer like versions of Z3, the Rust versions of them, they all, at least the one I use, like uses the libraries, the C++ libraries, but like has the Rust interface, and they're pretty cool. It's pretty cool. So I solved yesterday's puzzle. Day 10 was Z3. We'll show that in the recap, just to kind of see how it works. I actually, it took me a little while to write because I'm still pretty new to using Z3. But I think I'd like to do like a little tutorial on how to use Z3, at least to learn for my own self. If you're interested in that, maybe we can do that together. So that's where we're at, because I do like, I want to kind of try and keep most of this focused on puzzles, but like also just learning. So I have ideas to like do some computer science style courses. Apparently YouTube has courses, so make like courses, especially my kids are interested in programming. Wow, what better way for me to like teach them, make videos that they can watch, and then I can help them with stuff. So, and you all can benefit from that as well if you're interested in it. So anyway, that's where we're at. That's where the day is. Let's talk about the problem. Okay, so you climb down, and like it looks like you're in like a reactor room, but it looks like it's like an IT type thing, right? Because they have a bunch of server racks and a bunch of like cables running from different server racks to the reactor and going all over the place, right? So you can think about like all the machines and then all the network cables as like uh part nodes and edges to the graph, right? Nodes and edges and um and they're trying to they want to they're trying to like discover like there's some problem with some of them, and so they want to like find all the distinct paths from, in part one, from you, the server marked you, to the end, which is out. So you can see here you have like kind of this graph, and it's saying, okay, we're gonna create this graph, and you're gonna go start at you, and you're gonna look for how many times you can get to out. This is an interesting problem because it's not just saying, can you find the shortest path to out, which we've covered before, and it's like a Dijkstra type thing. It's saying how many paths are there from you to out. That's what it's asking. So if you look at this one, you can see like there's all kinds of connections that lead to out, and in this case there's like 5 different ways to get there. So even though if you look, there's only like 4 nodes that connect to out, there's multiple ways to get to those nodes, and I'll show you that in a second. But that's what it's asking. So you're going to start at U and you're going to traverse your way through and get to out. Part 2 is similar, but now it's like much more expanded. We'll talk about that. But that's the problem in general. So how do we go about solving part 1? Well, again, I mentioned, I think this, I pretty quickly came to the dynamic programming solution for part 1, because I suspect if you look at the input, it's pretty clear that the graph is large. So here's the input. The test example is very small, and you could probably solve the test examples in any way you wanted to. Like you could literally just do a breadth first search of the whole thing and like solve these efficient enough that you would like get to a solution at the end, right? Like this graph is relatively small. The way this graph looks a little funny, I'm sorry, I tried to figure out a good way to do it, but imagine green is the start, red is the end, and like these are the middle nodes. I tried to do them like in order of rank from like U to out, so it would be more obvious. Like, so these 2 nodes right here are connected to U. These 3 nodes are connected to these nodes. And you may ask yourself like, oh, well, why did you do it that way? Well, it's very explicit. It tells you data only ever flows from a device through its outputs. It can't flow backwards. And so that and there's some other place. I can't remember exactly where it is, but essentially it's telling you it's a directed acyclic graph. And what does that mean? It's always flowing from one direction to the other. And so that should help you get to oh, well, if it's always flowing from one direction to another, that, you know, I don't have to worry about cycles. You can think about, there's like arrows right here, maybe. Well, you don't have to think. There definitely are arrows like right here and right here, right? It's always going from here to here, and there's never a node that says, oh, go back here, right? So that's really helpful, I think, in solving this. It's like directed and acyclical, meaning it's always going to flow in one direction, and it may get really large in the middle, but it will always start at one direction and go to the end. And in fact, if you look at the puzzle input, here's the actual puzzle input. You can see there's a lot of nodes, but it always starts at server SVR and flows this way to out. Your nodes, the nodes we're interested in, these we're interested in for part 2. This is what we're interested in for part 1. We're actually only going to start here for part 1. And so the question it's asking us is, how many paths are there from U to out? And you can see there is a lot. There's a bunch of them, right? This is small enough that you could probably calculate it again with like just a straight up BFS, like just search all the paths till you get there. And the reason I say that is because the growth, you can see like the growth here is like exponential. And what do I mean by that? Every node on like this, every node on this rank that's connected to this rank has a multiplying factor. So let's say that like there's 50 here and there's 70 here and 500 here or whatever. If this node connects to each of those, it's like the sum of these. So it's not exponential, it's multiplicative or whatever, right? So it's the sum of these, but then this one up here is like the sum is going to be connected to all of these, right? Multiple branches. And so it's just going to be explosive. And you can see the answer to part 2. It's huge. It's absurd, the number of like total potential paths you could take. And okay, so the reason I say that is because you have to start thinking about like, oh, well, how am I ever going to solve that efficiently? And so let me just describe like the thinking that allows you to do the dynamic programming. Obviously, the graph theory is like interesting. Like we know it's going one direction. it's a directed acyclical graph. So we know it's going one direction and there are no cycles, right? Or we know it's going a way. You can't flow both ways is the way to think about it. And we never get a cycle. We never come back on each other. That can happen like traversely, right? Like there's always arrows is the way to think about it. Because if there weren't arrows, think about it, you could actually get to U again by going to this node and then going to this node and then going to this node and then going to this node. That's not the case though, right? The way the puzzle input has been given is you'll always go from this left rank right here to this rank to this rank and to this rank. So you'll always be flowing this way. I hope that makes sense. Okay. And again, this graph isn't super perfect because I actually think obviously this one and this one out should probably be over here, and then like there should be like some weird lines. But anyway, I hope you get the point of the graph part of it. So then the question is like, how do you solve this with dynamic programming? Remember what dynamic programming is can you take a large problem and just solve it with a smaller problem? And in our case, the question, the large problem we're asking is how many total paths from U to out. Maybe I should write the number of paths from U out, right? And but if you think about it, that question, to answer the question how many paths from U to out, what we really need to answer is how many paths from A to B. So the paths from how do I say this? The paths from U to out is actually equal to the sum of A to out and B to out. So we really just have to solve that problem. We just have to know how many paths are from here to out, and we can do that recursively, right? So let's actually do that. So B2, and then we'll label these C, D, right? So we need to know what A to out is and B to out is. And in order to know A, we need to know C, D, and E. And in order to know B, we need to know D. Well, we can actually solve C. We know there is one path from C to out, right? So there's one. We know there's one path to D as well, right? In order to know E, we need to know how many paths to F. It turns out there's one here. So how many paths are there from F to E? There's just one, right? Because there's one single line right here, okay? And so now the question is like how many paths are there from A? Well, it's the sum of the number of paths from C and D and E, right? So we know there's one path here. How many paths here? There's one path here. How many paths here? There's one path here, right? So we know that there's 3 total paths. Am I doing this right? Here. And then there's one path here as well, right? And then there's one path here. So we know there's 2 paths here. So how many paths from A to B? There's 5 paths. Did I do that right? Let's check. Yep, there are 5 different paths. There you go. So, woo! The point of all of this is to say, just think about, and this is a much simpler graph, but I think this is interesting to think about. And you may be saying to yourself, oh, well, how did you get these numbers? Again, remember, we're just counting backwards, right? So I'm going to do it one more time. In order to get this one, we need to know these 2, right? In order to get this one, we need to know these 3. In order to get this one, we need to know this one. And so we're going to start on these ones connected here. So we know there's one path this way, there's one path this way, and one path this way. And now let's just keep working our way backwards. There's one path this way, there's one path this way. There is one path along this line. There is one path along this line. There is one path along this line and one path along this line. So now we have A has 3 and B has 2. So this one is the sum of those two. 3 plus 2 is 5. We're just working our way back. And I'm not going to do it, but you could potentially do it on a graph this large, right? You know there's one path for each of these. There's only one path for each of this rank. You know that this rank will always have a path of 1. But these will have the number of connections. So like say, and this isn't perfect again because there's like directionality to it, but you can kind of see that like this way connects. And some of these have like few or no connections, right? Going this way. Like, so maybe this one will only have a couple. So this one will be 2, but this one may have a lot. So maybe this one has 20. And then you're just going to keep doing that, counting it this way. Now, the thing that you're only like, maybe the way to think about this is now you're only like visiting each node once. Because if you ever ask yourself, like after you've solved this is 20 and this is 30 and this is 10, when you're like up here and you're saying, or maybe right here and you're saying, well, how many pass to this, and it's this plus this plus this, you don't have to go consult those things again. You already know it's 20, 30, and 10, so you know that this one is 60. That's all you have to do. So you can use that dynamic programming to like help you solve a big problem by solving a small problem. And that's kind of the power of dynamic programming, right? So how does that look in code? Well, first let's parse our input. So we're going to create a hash map from the node to its neighbors. So we're going to map any node to its neighbors. It's going to give it to us, so we know exactly what they are. There's nothing much special about that, but this is like the kind of like the lookup, right? That says, oh, what are my neighbors? Who are my neighbors? And then here's the dynamic programming part. But assuming we've solved the dynamic programming part, we really just call the dynamic programming from U to out, saying, hey, get me the number of nodes or the number of paths I can take from U to out. And what does that dynamic programming look like? Well, that's right here. We need our neighbors list. We need our paths. This is like our memoization or our scene list. This is like telling us if we've seen this one before, don't try and go down that path again. And then we need to know what our current one is and what our end state is. Where is our end? In this case, I think it's actually always out, so maybe you could omit this, but this is telling us if we're done. So now we need to do our like base cases in our dynamic program. Have we seen this path before? Or this check before? If we've already calculated the paths, we just can return that value, right? So that's what that does. We look it up in our paths. If we've already seen it, we don't need to count it again. We can just return that value. If we've reached the end, then that means we're done, right? We know we're done. So we found one path. And so we just return 1 for that path. Otherwise, like I said, what is the number of paths? Well, it's equal to the sum right here, right? The sum of the paths from each of the neighbors. So I get the neighbors of cur, and if they exist, if they don't exist, obviously I return 0. There's no paths. But if they do, I'm going to go through all of the neighbors and call recursively my dynamic programming function and say, well, get me all the paths from next to end. So this is also like a DFS with memoization is what it's been called before. So you can call this DFS with memo. It's a dynamic programming solution. The idea is we're taking a big problem which is how many paths from here to here, and breaking it down and saying, oh, well, I actually, and it is a DFS because we're going to go all the way down and we're going to say, okay, how many paths from here to this one? And then this one, this one, this one, and then that will help me solve these ones on this rank, and then that will help me solve these ones on this rank until I get to that current node. And now I just, like I said, all I need to know to get my current one is what is the sum of it, the distance or the paths from its neighbors, and I just add those all up. That gets me the solution to part 1. So there it is again. I hope that makes sense. That's a great way. That's what makes this thing, I think, in my mind, relatively easy to solve, is if you can think about it from a dynamic programming perspective. I think you need to know the graph theory part of it to say, oh, it's directed and acyclical, so I know I'm always going from left to right. That means I can efficiently do the thing. If it was different, that it would change the problem a lot, right? Especially if there was a cycle or undirected, like you could potentially have like weird, you could go different ways to get there, and it would totally change the problem. So I think it's clear that it was like intentionally like, here's what it is, and that should lead us to the dynamic program. Now, let me just say again, if you didn't get there quickly, don't worry about it. Again, I've been doing graph theory, and it occurred to me as I was prepping for this video and I was thinking about what I might say. Most of my actual day-to-day work at my job is graph theory. And it may sound funny because I'm not in like a social network thing, but the data that I work on is inherently a tree in nature, which is a directed acyclical graph, a type of one. It just doesn't, like, this problem actually folds at the end into a single thing. But anyways, a lot of the work I do is very graph related, even though I don't actually do graph traditional things that you'd think of like graphing as like a map or a social network type thing. So I've done this a lot, and so the problem felt easy to me, but I don't think this is an easy problem in general, right? I definitely would put this one in the hard category. Like if you were to look up a problem akin to this in LeetCode, even the part 1 would probably fall under the hard category because you do need to know some stuff. I guess maybe the part 1 falls in the medium category, because you could depending on the size of the inputs is what changes it, right? What can you just do a BFS to check them all versus do you have to do dynamic programming to solve it? Anyway, this is all to say, I hope you know we're all in different places, right? So when I say this part 1 and part 2 is easy, don't think that like makes you like a terrible person or something like that. We're all at different places. Yesterday's was a slog for me, today's was not, and it's just like that for everyone. Okay, so hopefully you understand though what we're talking about here. So let's move on to part 2. What does part 2 say? Well, they think the problem is actually in the DAC and the FFT devices. So we have our network, and now they're saying, oh, we think it may be these 2 devices. And what they say is, now we want you to find all the paths from the server, SRV, to out, but they must also visit the DAC and the FFT nodes. And so they give you actually a new input, and they show you, here's all the possible paths, but only 2 of the paths, these 2 paths right here, visit FFT and DAC, the DAC, the FFT and DACs. So there's all these possible paths, but only 2 of them are actually valid because they visit both of those places. Okay, and that's what changes in part 2. So it's still a graph thing. It's still you know, a DP problem, I think. But what you're trying to solve now is you only want to include paths that include FFT and DAC. So how do you go about reasoning about this problem? This part 2. Well, again, a lot of this hinges on graph theory. But if you think about the nature of a directed acyclical graph, and they're telling you that you have to visit like 2 internal nodes, that kind of suggests that there's only possible two possible scenarios for your graph. And let me show you what I mean by that. Here's the actual graph if you spit it out, and you can see like the only way that you're going to visit all of these is if you go this way, and then you if you visit here and then here and then here. That's to say, like, the path that you're going to take is going to be SVR to FFT to DAC to out. And this is because it's a directed acyclical graph. There's that's specific to this case. The only other way you could do it is if it was DAC to FFT to out. Like, these are the only 2 paths. Or what? How do I describe that? Not the only 2 paths, but the only 2 like path groupings or something like that. Path. It may be like the pathing order. Like, maybe that's the way to describe it. These are the only 2 pathing orders you could take, right? Think about it for a second. Like, if I start here and I go up this way and here and here, I can never go to FFT again. So I go here, maybe I go here and hit DAC and then eventually get to out. There's no way for me to visit. What I'm saying is in this specific graph, there's no way for me to visit DAC first and FFT second. Like, that's just never going to happen, right? I'll never be able to do these 2 ways. However, you could get a graph. You could create a graph where DAC was first and FFT was second, but it's always going to be in that order. And that's, I think, the key to understanding that this is a directed acyclical graph. There's going to be a very specific ordering. A path ordering is the way to think about it, right? So it's always going to be one of these 2 cases. It will never be both cases. If it was, it could not be a directed acyclical graph. I hope I'm explaining that's okay. I think that's the key to understanding part 2, is because it's a DAC or a DAG, we can infer this information from that. We can derive this information from it. We don't have to defer it. We can actually derive it, right? And it's only because the puzzle is saying you have to visit these 2 nodes, right? So because we know we have to visit these 2 nodes before we've gone from, like, we always start here and we always end here, but at some point we've had to touch like one of these and then one of these to get to here. And that's what allows us to say there's only 2 options. It would be more complex if there was 3, right? There would now be 3 orderings that we'd have to be interested in, right? But they've only given us 2, so we know there's only 2 ways to do that. We do FFT first and then DAC, and then we do DAC first and then FFT, and that gets us to the out. So why is this helpful? Well, if you remember, we've already solved part 1 with this efficient solution, the dynamic programming, where we've said, if you give me any start position and any end position, I can efficiently tell you how many paths there are. Well, we can just try. Why can't we do that for each of these, right? Right here. So why can't we just say, well, how many paths are there from here? And then how many paths are there from here? And then how many paths are there from here? Right? So let's say that this returns 50 and this returns 10 and this returns 10, right? We know there's 10 paths from DAC to out, FFT to DAC, and serve to FFT, right? So then the question is like, well, now we know the paths from each of those. How do we know the paths from the beginning to the end? Well, it's just the product, right? Like we had talked about before, if there's 10 to here and then there's 10 to here, then from here to here is going to be 10 times 10, right? Therefore, 10 from here to here is this times this. So what is the total path in this solution? Well, it's 50 times 100, which is 5, right? So that's where we know. We now know it's like the product of the paths from each of the nodes. The only other thing I want you to think about is like there's no way for you to, well, there is a way. You can use an algorithm to find out which one of these is correct, right? But the way we're solving this is actually so efficient that I actually only one of them are going to work, right? It's clear that only one of them are going to work. So one of these is going to say there are 0 paths, right? And it's because if you can't go from server to DAC, DAC to FT, and FT to out. So one of these in the middle here is going to fail, and it's going to return a 0. So if this one worked and this one didn't work, it's going to return 0. So all we have to do then is just return either this one or this one, the one that's not 0, right? Well, that's what I do in my code. So you can see I've solved P1 with this DP program. P2 is literally just me saying I'm going to try this path and I'm going to add that to this path. One of them is going to be 0, but you know, I'm going to try both ways, and I'm going to multiply the paths to each other. One of them's going to be 0, one of them's not going to be not, and I'm just going to return the solution. So again, why can we do this? So I'll try and read what this is saying here in the comments. The puzzle tells us is a directed graph. That means that there must be one of 2 paths between the interesting nodes, because we're only looking for those 2, right? So it's either this one or this one. And so we basically just say, find each of the paths, or find the distances from here to here, here to here, here to here, multiply them together, and add that to the distances from here to here, here to here, and here to here. One of these is going to be 0, and one of these is going to be this absurd number, 100,000 billion, trillion, 511 trillion, right? So one of them is going to be 0, one of them is going to be 511 trillion. By the way, that number is why you can't do like a BFS, right? You just use up all the memory on your hard drive. 511 trillion of anything is too much. And it would never finish. And even if it did, you'd have an AWS bill larger than you'd ever be able to pay for, I think. But the point of all of this is to say, once you've kind of figured out the dynamic programming aspect of it for P1, it just becomes this. And you can actually see, like, if you remove all the comments, the solution to this problem is absurdly small, right? We have a DP function where we do an if check, a sum, and then return our solution. And then for P1, we literally just call that from U to out. For P2, we just call it for 6 times and multiply the results of the one direction versus the results of the other direction, and add those together to get to the answer. That's what I think is so cool about DP and solving. So anyway, I hope that makes sense. Again, like when you're looking at this, there's only one way for you to go through the graph, and that's, I think, the key to solving this part, is recognizing that there can only be one way. So that's why I say, is part 2 hard? I definitely think so, because you have to know enough about graph theory to say, oh, there's only one path through this, and so I can just solve this efficiently by using my DP from part 1, but trying both of those paths, right? Again, if it was slightly more complicated, you could do a pathfinding algorithm to figure out which one of these is accurate. Like, say there were 5 of them. Well, now you have like whatever, 5 factorial ways to do it, right? And that's not enormous, but it is large. What is that? 20, 60, 80? Like 80 ways, is that right? Oh no, 120. I multiplied incorrectly. It's one, there's 120 different ways to do it, but you could still do that, try the 120 different ways and like find the correct path. There will only be one correct path that will allow you to go through it. And then once you've found that correct path, you just multiply the, you just run your dynamic programming on them again. So, the two made it very simple to just say, oh, I'm just going to try the two and solve it. If there was more, you might have to say, okay, maybe I'll do some path finding in this, like figure out what the right one is and solve it. But even that at 120, you could probably just parallelize all 120 of them, solve them quickly, and be done with it. It's only if there was a bunch, right? That maybe then it gets harder. But there you go. I hope that makes sense for P2. This was me going on a weird tangent of saying, if you understood graph theory, if you've done dynamic programming before, this day was probably easy. If not, hopefully I've helped you understand how dynamic programming can be powerful by taking a large problem and breaking into a smaller, and then just recognizing that we got to understand, sometimes to solve these problems, you got to understand graph theory or linear algebra. And so if you don't know those things, it's going to be hard. But if you do, it's not going to be too bad. Okay, so what do we learn about today? Again, I think maybe it's not a super hard day for some people, but it will be a super hard day for others. And it's, do you understand graph theory? Have you done a lot of dynamic programming before? Then it's probably painfully obvious, right? So let's look at go back to the 20. There you go, perfect. This is exactly what I was talking about, right? It's going to be, if you've done graph theory before, you will immediately know, oh, it's a directed acyclical graph. I can use dynamic programming to solve this. And then for part 2, you're all like, oh, there's only 2 options, simple solution. So perfect. Day 8. Day 2, day 10, part 1, terminal tour. Oh, no, we're on day 11. Yeah, you can see how crazy the lines are, right? There's a lot of connections, so you definitely have to do some stuff. Okay. Writing an algorithm to prune possible paths for data, changing the start node and end node 3 times the part 1 code and multiplying the answer with. That's totally the answer. That is totally the answer. By the way, I visualize this, right? I use some code to visualize it, to look at it, and I think that, I think you could see that you could solve, if you know enough about graph theory, you can solve this problem without it. But I wanted to visualize these purposefully because I think visualizing it helps you see what's going on, right? It helps you see that, oh, so why isn't this graph helpful? You have to understand the directedness of it. So if you look at my like visualization code, it does it in ranking. We kind of start at one node and find all of its neighbors, and we put it in the next thing, and then we find all of those neighbors, put it in the next thing, like this. Ignore a lot of this because it's like AI autocomplete and stuff like that. Yeah, organize them by level, right? Like this is what we're interested in, is we're going to like find levels and organize them, and that's what's going to make the graph readable, right? So that's why like this is no longer readable, but like you can kind of, see there's like rankings of going through the process. Same thing right here. There's definitely rankings of going through all of these, right? There's going to be connections that look like they're going backwards and forwards, but it's always going in from this side. The graph is always going this way to this way. And so you can act, if you rank them like this, it really, I think it helps visualize, oh, here's what's happening. And here's why part one might have been fairly easy to solve. I think I said this, fairly easy to solve with any solution, because the number of nodes to get to here is actually, you only have 1, 2, 3, 4, 5, 6 ranks. So even if the connections are large, relatively, it's like a densely connected network, you'd still like get a comparatively small number. That makes sense. Well, in fact, we know what the number is. It's 570, right? So it's a small number of paths you can take in this thing, even though it's like going up and up and up. However, that changes a lot when you're way over here. You go from 571 here to 511 trillion here, right? Even I may have even done that number wrong, but that's the point. In any order. Oh, well, it can only be one order. That okay, I see what the trick is here. If you read the problem and it says any order, that is true. For each input is maybe the way to think about it. Is like, I don't know which way your input is. I think mine was definitely, well, we can look at the graph again. Mine was FFT and then DAC. So that one produced the solution. When I tried DAT to FAC, it would have given me a big fat 0, unsolved. Okay, so yes, I can see in order. That was technically a lie. Because it's a directed acyclical graph, your input will have one specific order, and you just had to figure out which one that is. In my case, I didn't care to figure out which one it was. I just said, I'm going to try both. One of them is going to be 0, so I'm just going to add them up. I already visualized in graphism, spot the green connect key nodes, and searched. 6 group served, 5 key nodes. Yeah, so there are sort of key nodes, but what that's really saying is like, you can see there's some rankings right here where there's substantially fewer like nodes, right? So right here, this first rank, there's only 4. There's only a few in some of these, and those ones like are key. And because you have to go to FFT and DAC 2 out, some of these nodes may not lead you to these places, and so they may not, that you can kind of skip them and ignore them. So maybe that's where this is getting at, is like, if you skip and ignore the ones that aren't there. Yeah, you'd have to look at the code to like actually see what's going on. But anyway, that my suspect is, if your answer is too high, you're probably not filtering by both. But we'll see. No valid presses. Oh, that's day 2. That is true. If you read the actual problem, the one next to you is labeled U, which is kind of funny. FFT DAC out. Serve FFT DAC out. I'm just curious, was everyone's serve FFT DAC out? It's possible it was. Like, notice it's hard to see here, but there's only like 5 lines coming out of FFT going this way. It's possible there's fewer. So like, obviously the graph goes this way, but that means that there's only really like 4 or 5 nodes along this that are actually interesting. So, these cables are quite a mess. Yeah. Ooh, sometimes when you get like the networks racks that are like perfectly ordered, in or yeah, that's not the. It is funny that they say that, but I suspect he's saying that because for your input it may be swapped, right? But for any one graph, there was only one path through it. It's not a graph flow problem, so I don't suspect so. Yes, what this person is saying is correct. Oh, this is a they did Everybody Codes, so we got to see a lot of their solutions in Everybody Codes. I think they were doing Rust for Everybody Codes, and now they're doing Odin. I'm sorry, I'm loving Rust, so I haven't had a reason to try another thing. No, it's not a flow, and I do follow Rust Jerk just to keep myself humble. Flows are solved. Capacity constraints. There are so yeah. So it is not an actual flow problem. The way this Edmund Karp solution works is like when you're thinking about flows, it puts constraints on like which nodes you can visit and how to visit them. But in this case, it's actually the opposite, right? So okay, we're getting a lot of visualizations. And what is, oh, is this a porn joke or something? Graphic. Okay, it looks like there's a lot of, I think I've gotten through most of it. Okay, look for EP for part 1 and part 2. It's very cool to me. The simple cache can code trace brilliant paths of code. About our past far where we were, have we seen DAC, have we seen. Oh, that's interesting. I don't know. Okay. You could keep in your cache. Well, let's look at their code. I'm interested in knowing how that works. Part 1, I presume, is DP. How would you do the DP where you're finding both? Oh, your cache. You pass whether you've seen it true or false. Oh, did I disconnect from the internet? Oh no. Is GitHub down? After yesterday, I kind of feel the same way. Much easier. For me, at least, right? Yikers. Reddit's not down. Maybe just GitHub? Oh, that's gonna make it hard to look. Yikers. Okay, it looks like this will be a short video. At least I cannot get to GitHub. We see is down. Uh-oh. Uh-oh. Well, that was a lie. Was this in? No, this is. Oh, they've got Git operations back up, but nothing else is working. Okay. Well, bummer. We won't be able to look at a bunch of solutions. But I mean, we can still kind of read these. So I suspect what let's go back to the cache can convert code that traces 5 trillion into code that forgets 20 things. all you need to remember past so far is where we are, have we seen DAC, and have we seen FFT. Yeah, so I suspect if you do the DP with the like that's not my code. So you do this DP, but then you say, but you include in your position, like, have you seen DAC and FFT? And you only, if you, once you get to the end, you return 1 if you've seen DAC and FFT is true. But then you otherwise, you, if you get to the end, if you've seen DAC and FFT, you return 1, otherwise you return 0, and then you do that. So should we compare and contrast that solution? Just really quick. Call it also. So if we've seen this before, we return this. If per equals end, and then we say if seen that and e true, return. Cool. And then down here, we call neighbors.get, and we're gonna have to this say suitable. Back true. Oh, I actually don't want to. I think I actually want to do it like this. We're gonna do this, and we're going to do next end scene back or next back scene equals like that. That. Alt per is served in its out. Alt. This 0. What am I doing? It's probably my scene DAC, scene FF. Uh, this. Uh, why 0? What am I missing? Edges. Scene deck. Okay, maybe I actually don't know how to solve this thing. Please come on, GitHub. Oh, we're back. Yeah, so you can see you're just, if you found out it's 1, otherwise you do this. Cache part 2, scene. Or oh, I need to track. I need to track it in my paths. That's why it's okay. I won't try it. So why is it working for him? Because you need to like know if at any point in your, so this cache is caching whether you've seen DAC as well as whether the current node you're at, right? And so that's why that memo is working. I'm gonna try and fix it. This way may actually be faster. This may actually still not work either. Oh no, there it does. Okay, there you go. Okay, so that is a different solution, and it is actually faster. And why do I suspect it's faster? I actually do 2 checks, right? I'm going through the grid twice, whereas this DP is only doing it once. So there you go. Very cool. That's another cool way to think about it too, right? Is like if you're just tracking these 2 values, then you can, as long as you're memoizing your solutions, it works. So very cool. That's something good to think about. You maybe don't have to know enough about graph theory to like figure that part out of it, and so maybe there is another way to do this. I still think graph theory probably helps for you to be able to do this, but Okay, this was a nice breather. Okay, the cached crate is very interesting. Walk paths. If it's out, 1, otherwise 0. Walk past part 2. Okay, this is very much like the Python solution we just saw from Paulson, right? Where it's kind of like tracking whether you've seen both of them and caching the responses. This cached crate is kind of cool because it is the essential same thing as like the func tools cache, right? This one in Python. So that's essentially what it does is it says if I can put this in a hash set, I so you have to be able to, all the parameters of the thing have to be like hashable, but if they are, then I will keep track of the results. It's basically going to wrap this function in the results, and so that's a cool tool. I think we've maybe used it before, but like years ago. So I try not to do it because it's nice to, in my mind, to see the memoization. Uh, okay, let's look at the solutions, see what they did. Okay, so these are maybe like interesting nodes. Either these or some new ID. Okay, so this, I think what's happening here is you kind of like, the idea is, can you turn the graph into a set of nodes and like names? And the thing about this is like, then you can like say, oh, I don't need to actually know the name, I just need to know the ID. And maybe that helps with like the string part of it. So you can see here I have a lot of like lifetimes for my strings. Sometimes that can get a little complicated and ugly, and so it might be easier just to treat them as an ID. So each node has an ID with its neighbors. And what this allows you to do now is, so what they've built, what I have is I just use the actual grid as like, or sorry, the input as like my mappings from node to its neighbors. But they've actually built out now technically an entire graph, right? So now you can traverse the graph using like more traditional, like what are my neighbors and things like that. So very cool. Yeah, so part 1 again, so what they're doing is just a DFS over, and they're keeping track of which one are visited. Presumably you'll know if you visit it, you already know the answer, and then you just count going down. Okay, very good. Yeah, I think it's just count with dynamic programming, probably the part. So what is meant by high degree nodes here? Like, it's like nodes that have lots of incoming, lots of outgoing. But again, I think if you just treat it like a DP thing, it gets there. But I like the solution. You like guess the high degree ones, and then you do a DFS from each of those to form like a smaller graph. We've seen this before. Well, we just did, remember how we did like the grid compression? Essentially, this is doing like a graph compression and saying like, treat these like higher order nodes as like big deals. And then you're really only interested in like each of the things to those specific ones, right? So you're turning like a very big, how do I show it? And this won't be accurate, but what you do is you then say, okay, well, let's keep these 4, but let's only do these 2 right here. And then like, or maybe there's 3 or whatever, right? So now the links look more like this. But these 3 are like, have these numbers in them. And so now you have like a much smaller graph to deal with, I think, is the notion of the idea here. So simple DFS with memo part 1, triple DFS with memo part 2, or 4 if they're no. Okay, so I suspect this one's very similar to mine. Yeah, so it's trying each of them, it looks like, each of the paths, and figuring out which one is the right one. Okay, let's look. Memoized path search, super fast. Good. Yeah, I think if you figure out that you can kind of memo it and DFS, it probably solves it. Yeah, there you go. Try path 1, try path 2. One of them is right, add them together. One of them's not and will be 0. There you go. Yeah, no, you actually can't reuse the memo here. So notice how they do clear after each of these. It's because like again, it's the graph is directed. So like one of these is going to produce like incorrect results, and once it produces incorrect results, like well, by incorrect I mean it will be a big fat bunch of zeros, and so uh you'll no longer get the correct answer. So you have to kind of like use a new memo on each one. Memoized recursion. There you go. Very good, very good. Okay, here's a cool way. You can just say like, how many paths are there from DAC to FT? And if it's 0, you do it one way or the other. So that is an interesting optimization. This is a quick way for you to tell which one is correct. Remember, I said like there's only 2 options, right? The paths are only going 2 ways. So this is a cool way to just say, well, which way's the right way? And then you can calculate the rest right here if you need to, and multiply them together, return the sums. Again, it would be a lot harder if there was like, say there's like 5 internal paths. Now you need to like, what was the number, 120? There's 120 possible ways that the graph goes. But again, I think you could just wrap this around and calculate it, right? You could wrap around and just say, okay, well, which one of these is correct? You'll find the right way. What else? Recursive DFS with memo splits the route into 3 sections. 2 size indices so that we can back as cache. Faster than hash map. Okay. I presume a lot of this is the same. I probably should have. I actually was just happy that the day was quick and done, and I'm like, okay, let's get to this. but it would be fun. This one would be fun to optimize because the day wasn't actually, at least for me, it wasn't difficult. And you can even here, you can see it's like 45 lines of code to like solve the problem, right? There's no tests in here or anything like that. But the actual solution, I mean, we can count lines because it's so small, right? Is like, this is technically one line. Then we get like 3, 4, 3, 6, 7, I don't know, 15, 30 lines of code tops. Yeah, if you get rid of the comments and you're trying to like golf it or whatever, which I learned about recently, like minimize the lines of code, you can, this solution you can get down really small. And it's because of the nature of the problem. I think that's what's interesting about dynamic programming, recursion in general, is the problem seems almost intractable in your mind until, I've said this a million times, it doesn't feel like it makes sense until you break it down into like, can I just solve a piece of the problem and then use that recursively to expand to solve the problem as a whole? And then suddenly it's like 5 lines of code solves a very complex problem, and it feels like magic. And so that's what's cool about dynamic programming in my mind. Okay, I don't feel like, we'll go one more DFS memo. I feel like we're just going to get a bunch of, you know, memoization ones. Yep. Okay. I don't think we're going to get many other solutions than that. So very cool day, very fun. I hope you had fun solving it. Again, if you struggled, don't feel bad. These days are easier if you've been solving puzzles for years, like I have. But when I was first solving these puzzles, things like this seemed just impossible to solve. And you start looking for help. And don't feel bad about like asking the AI for help or coming to videos that have the solution to help you figure it out. I think that's great. Come figure it out, have fun, and look for different solutions too, right? That's why I do all this at the end. It's fun to see what different solutions there might be so you can learn from those as well. That's what helped me. I'm like, oh, I should go check Z3 for day 10. And so learned a little bit about Z3 the other day. I think that's fun. Maybe I'll share it with you. Anyway, thanks everybody. I had a lot of fun. Talk to you next time. Bye.